Hello students, welcome back. As the optional video number 3 of the preliminaries, let's discuss equivalence relations in general and some examples associated to it. First, the equivalence relation. Just like functions, let's begin from Cartesian product, the set of all ordered pairs, and establish this as a well-defined expression. Start from the ordered pair, defined like this as a set, which is a member of the power set of a union. Yeah, I know, this is rather weird, but at least it's well defined because it's union, so it's well defined. So its power set is well defined, and its power set is also well defined due to the axioms of set theory. So everything makes sense. Everything is well defined, and consequently we have the Cartesian product expression like this as a well defined set. So all is well defined, everything is great. So the Cartesian product concept is now rock solid. And now from here, we define a relation as any non-empty subset of a Cartesian product. Important examples include a function, an equivalence relation, and an order relation. Now for this course, order relation is not that important, so let's not worry about this. As for the function, we already discussed it in optional video number 2. So that leaves us equivalence relation. Let's discuss this a little bit more detail. Okay, here we go. An equivalence relation is a relation on X with these three properties: reflexivity, symmetry, and transitivity. If you prefer set theoretical expression, you can do it like this. It's a relation on X, so instead of X cross Y, we have X cross X. And then it's non-empty, of course, because it's a relation. And then we can redefine reflexivity and symmetry and transitivity like these, as you can see from this set theoretical expression. But that's a bit too cumbersome, so we use these expressions, but they actually mean the same thing. And then as for the equivalent relations, we have something called equivalence class, the set of all elements that are related to a certain starting element A, which we call a representative, and that's called an equivalence class of the starting element A. And it turns out that the starting set capital X can be written as a partition, that is, a disjoint union of equivalent classes. The reason is like this. The equivalent classes can be either identical or disjoint, black or white, no gray. So the representatives are related, then the equivalent classes are identical. They're not related, then they're completely disjoint. Nothing in between. So if I take the union of them all, then of course all the elements of X will have its own equivalence class and it'll cover everything. Yes, so certainly this union of all equivalent classes will cover entire set X, of course. But then again, because of this, there's so many duplicates. So you can discard many of those and then take only one of those and then rearrange as x1, x2, x3, and so on. If you do that, then they're all disjoint because of the second property. So we end up with a partition like this, which we call an equivalent partition. And once you have an equivalent partition, you can consider the set of all equivalent classes, which we call a quotient set. Now, this quotient set can have the cardinality much smaller than the starting set in some cases. The reason is because we are taking the equivalent classes and there are so many duplicates. If there are really a lot of duplicates, then because of that, even though we started from every single element, X, from capital X, we trim out so many that we end up with very few distinct xi classes, and consequently this quotient set may have significantly smaller cardinality compared with the original starting set X. Please remember the property when we go over to the last example, modular equivalence. But that'll have to wait. Before that, let's consider these examples. How do we establish the sets of numbers? Well, let's begin with the set of whole numbers. Using the set builder notation, not set builder notation, it's the other one, the roster notation, we define 0 as the empty set of 0 element, no element, and 1 as, well, the set which include only one element, which is empty set, and then 2 as pairing the previous numbers, and then define 3 as listing all previous elements, and then 4, likewise, all previous elements. Continue, then we can define K inductively as a set obtained by listing 0, 1, 2, 3 all the way up to K minus 1. And continue over that. And inductively, we can cover entire whole numbers. If the inductive definition is possible, of course, but we have to start somewhere, so that's one of the axioms of set theory as a matter of fact. This construction yielded another observation, that is a successor operation. We define n plus 1 as union of n and this set n, so that 0 to n minus 1, and then union one more, so that you get 0 to n, and that's how we get the next number, n plus 1. And we can consider it as the definition of the next whole number, but also you can consider as addition, adding 1. Now, if you repeat this successor operation, then you get an addition, n plus k. Now, if you repeat addition, you get multiplication. Now, if you inverse addition, then you're going to get subtraction. But then again, that could cause a bit of a problem because the whole number system is not closed under subtraction. As a matter of fact, the additive inverse does not always exist here. So how do you define the set of integers from the set of whole numbers so that the subtraction is well defined? Well, we use an equivalence relation. Defined like this. Start from a pair of whole numbers, and then we consider certain equivalent relation among those pairs so that a comma b is equivalent to c comma t if a plus d is equal to b plus c, like this. And this a comma b corresponds to a minus b as a matter of fact. Here's an example. 0 comma 2 is equivalent to any n comma n plus 2, and that equivalence class is defined as negative 2. And then positive 2 is defined like this, and then you can consider you can identify the set of whole numbers with these kind of the second kind of equivalent classes, you see, n comma 0, and then take these as negative whole numbers and then put everything together. That's how you can define integers. Kind of tricky? Well, the embedding process can be a bit tricky to understand. You see, you started from whole number, which is different set, and then the set of integers is actually a subset of, no, it's actually not even subset, it's a quotient set of w cross w, but somehow w is considered as a subset of this quotient set through appropriate identification and embedding. That's a bit weird, but And that's another a week of discussion in the set theory, so let's not worry too much about that. What we did get is the set of all integers obtained by a quotient set of some cross product of this, the Cartesian product of this whole numbers, so that everything is well defined. Eventually, that's the whole, everything is well defined, you see. Let's see, did I prepare some further example? Oh yes, these. 0 minus 2, 2 minus 4, 7, 9, all those are the same actually. So you could select this 2, 4 or 7, 9 as representative, but most of the time 0, 2 is most convenient, and then we just define negative numbers like this and positive numbers like these. Let's use similar ideas. This time start from integer cross non-zero integer, because the denominator cannot be 0, and then we consider an equivalence relation defined like this. The proof whether this is actually an equivalence relation is left to the students, and then if we do that, basically we are defining a fraction a over b, like this. Here's an example. A fraction 4 over 3 is defined as the equivalent class 4, 3. In other words, 4n, 3n for any non-zero integers. If you have 0, then 0 over 0, you get nothing. This kind of thing corresponds to reducing the fraction in the lowest term. And then what if this second component is 1? In that case, we just get the integers back. So we use appropriate embedding and we identify a set of all integers like this kind of form, so that we can consider it as a subset of Q and go from there. And then another buildup will create the set of real numbers. This time, just considering a pair will not do. We have to get an infinite sequence, and infinite sequence of real numbers, infinite sequence of rational numbers with some condition. They will have to be bounded and increasing. You see, unbounded, then they'll all go to infinity, so meaningless. And then why do we have to have increasing? That's a kind of story that we'll have to discuss in real analysis class. Bounded increasing sequence always converges. There's things like those, and that's what we're going to establish here. And let's consider some example like this. 3.141592, etc., in decimal expression versus 11.01101, etc., in binary expansion, and 3.11037, etc., in octal expression, and so on. They're all the same. They all converge to same real number, pi, and we can consider not just pi but everything as a sequence of bounded increasing sequences. And then if you have terminating sequence, then that's a rational number. If it is not terminating, then we are going to get a irrational number. Again, the main idea is equivalence relation and quotient set. You see, two real numbers are same if they approach the same number. In other words, the tail part of the sequence converge and meet together. And that's how we define all those number systems. Complex numbers, that doesn't really require any kind of equivalence relation, as a matter of fact. It's the same as just R cross R with appropriate algebraic rule, which will generate I. And this rule here will suffice, as you can see in this example or that example. So what did you get? We got all those sets of numbers straightened out, starting from the equivalence relations. And all those will serve as integral tools for algebra as well.